Alright, so we're going to answer a chemistry exam question paper. So this is coming from second semester and second semester exam. So in the description I've provided information about the source of the university where it comes from. Okay, suitable for everybody who is trying to like have an idea on how questions in chemistry for first years in university actually come. Okay, so we'll start. Question 1. The decomposition of ammonia to nitrogen and hydrogen proceeds as follows. Okay, so this is coming from chemical kinetics. Alright, so let's get into it. So we've got this equation, ammonia um, being decomposed into nitrogen and hydrogen. Now we are told if the reaction is zero order and the rate constant is that, or the rate of the production of hydrogen, write the rate expression in terms of ammonia, nitrogen, and hydrogen. So under chemical kinetics, we've actually described how to write the rate expression. The rate can be written in terms of the reactant or the product. So the two things that we focus on when we're dealing with the rate is the change in concentration over the time, and then we put 1 over the stoichiometric coefficient. So if we look at the first one, that would be a 2. For reactants, we add a negative. The reason is simple. When the reaction proceeds, the reactants tends to reduce. So the rate in terms of ammonia is going to be negative 1 over the coefficient 2, change in the concentration. So these square brackets indicate concentration. So change in concentration of ammonia divided by the change in time. So that is for the first part. Okay, so we are taught to write it in terms of ammonia, and then in terms of nitrogen, nitrogen is a product with a coefficient of a 1, so won't make a difference. 1 over 1 is just like a 1. So just say the change in concentration of nitrogen divided by the change in time. Well, that is also equivalent to, for the other part, I can just write it down. For the other part, it's just going to be equivalent to 1 over 3 change in its concentration, that is of hydrogen, divided by the change in time as well. So that's the rate expression in terms of all the three. Okay, so in a case where they give you the change in concentration of ammonia, for example, and the time that it took, you're able to determine the rate. So in short, you should be able to determine the rate given any concentration and time of any of these, either the reactant or the two products. Okay, so that's for A. Now for B, we are asked to calculate the rate of formation of hydrogen from the above equation and also give the K value. Calculate the rate of formation of hydrogen from the above equation and the K value. Okay, so how do we basically go about that? There are a few things that we have to note here. We're trying to determine the rate of formation of hydrogen. At what rate is hydrogen forming? Okay, and then from there we also have to determine the K value. Now one thing that to note here is we are told this is a zero order reaction. Okay, so for zero order, if you had to write the rate law, our R is going to be, if you're new to the rate law, watch our video on chemical kinetics. The rate law has been explained. So the rate law is an equation that relates the rate R in terms of the constant K and also the concentration. Okay, so the concentrations of the reactants. So in this case, we only have a single reactant. Now, since we are told it's a zero order reaction, that means it's going to be the power. It's going to be power 0. So it just basically ends up R being just equal to K. Okay, and so therefore, if we are to determine the rate of this reaction, it has got nothing to do with the concentration. It's just equivalent to a constant, what? K, which we were given in the question to be 2.5 times 10 to the power negative 4. So the same units of the K will be equivalent to R in this case, because it's a zero order reaction, and as we can see, R is equal to K, so therefore the units will be the same. What are the units? Mole negative, liters negative, and second negative. Okay, so this is the rate of the reaction in general. Now if we are to relate it into the rate of formation of hydrogen, we have to go back to what we had written in the first part, which was A, right? We said the rate expression there was what in terms of hydrogen. So we said it was, that is 1 over 3, right? So 1 over 3 delta, that is the change in concentration of hydrogen, divided by the time that took. Okay, now the first part, this rate that we've written in the first place, this is in terms of ammonia. So for ammonia, what did we say? For ammonia, we say the rate expression is negative 1 over 2 change in its concentration divided by the what? The change in time. So for the rate expression that we had written in the first solution, which was A, the rates are equivalent. They are supposed to be equal. Okay. Remember, we had written it in terms of ammonia, nitrogen, and hydrogen. So those were actually equivalent. And so if you know of one, you should be able to make most of that and be able to find for the other side as well. Okay. So let's try to do something here. What can we try to do? We know that from what we're from the lateral where we said R is equal to K, we said the lateral is dependent on the what? On the reactants, and the only reactant we have here is ammonia. Since this is a zero order reaction, we said it's the power 0. That's one thing that we know, and so we ended up saying R is equal to K. So what we found was the rate expression, or the rate in terms of our reactant. Of course, we know there was no difference, but we know it was equal to K because of the power 0. So it was just 2.5 times 10 to the power negative 4. So that's for that part. Now I'll go, in this case, we want to find the rate of this guy. That's what we're interested in. Okay, so let's try to make that the subject. So if we make this one the subject, we'd have to multiply both sides by 3. We'll end up with a delta, or the change in concentration of hydrogen, divided by the change in time, which basically is equivalent to saying the rate, okay, in terms of hydrogen, is equal to, we're going to have, of course we'd end up with a negative, but we don't want a negative answer here. We'll just say let's everything be positive, so we'll have 3 over 2 change in concentration of ammonia over the change in time. So whenever you see the change in concentration over time, that is basically the rate that we are seeing at that point. Okay, what is on the left is basically representing the rate in terms of hydrogen formation. This part, that's the rate in terms of the reactant ammonia. So 3 over 2. Now we saw that using the lateral, we found the rate, well, for the reaction to be 2.5 times 10 to the power negative 4. Okay, of course the units are known. Grab your calculator. Okay, so 2.5 multiplied by 3 and then divided by 2 there. Okay, so my calculations here are giving me 3.75 times 10 to the power negative 4. The units are the same, more negative, liters negative, second negative. Okay, so that's it for question 1. Okay, so this is from Kinetics, and if you really want to know more about Kinetics, feel free to sign up on our site. The link is in the description below. You'll learn the topic in full detail, and all these concepts are covered comprehensively. Now the second question, let's read it. Ammonium hydrogen sulfide dissociates into ammonia gas and hydrogen sulfide gas. If we start with a sample of pure ammonium hydrogen sulfide at at 25 degrees Celsius. The total pressure of the gases is 0.658 atm when equilibrium is established. Okay, so this is from equilibrium now, as we can see. So the symbol there can be actually be written something like this. No difference. Write the K. So that's supposed to be the Kp value there. Okay, on A2. I was just trying to retype the questions properly. So I think when converting to the PDF as well, that happened. So write the Kp value. Write the Kp value expression for the dissociation shown above. So you're writing the K expression, the K expression based on that reaction. So what do you do? So what you basically do in such a case is this. Your Kp, any K expression is in terms of the products over the reactants. Okay? And for the K expression, please note that only gases and aqueous states are used when they are the only ones that appear in the K expression. Well, in this case we have gas and gas, right? So the pressure of what? The pressure of the products, which are, the first one is ammonia, okay? Raised to a stoichiometric coefficient, we just have a 1, and then multiplied by the pressure of the hydrogen sulfide, also with a stoichiometric coefficient of the 1, was in gaseous state, divided by the reactant. Okay, I'll assume, I don't know what I'm doing, so ammonium hydrogen sulfide. So that is not supposed to appear in the K expression because we can't find the pressure of a solid. So basically, also raised to the stoichiometric coefficient, but that is not supposed to appear. So it was going to appear if it was a gas, or okay, in this case for pressure. But of course, under the Kc expression, that's where we use now the aqueous states. So all solids or liquids will possess a value of a 1. So the Kp expression is just that, okay, in terms of gases. Now for B, we are told to determine the value of Kp now. So we now need to determine the value of Kp. Now what are we told? We are told in the question to say the total pressure of the gases is 0.658 when equilibrium is established. So we are told that equilibrium, the established pressure was 0.658 atm. So how do we determine the value of the Kp? So given that the total pressure is equal to that, we can come up with an equation here where I would say let A be equal to the number of moles of both, it may be ammonia or the hydrogen sulfide. So let A be equal to the number of moles of ammonia or hydrogen sulfide. So meaning that we are saying they have got the equivalent value, right, of the number of moles, since we've got 1 and 1. Okay. So the total number of moles therefore would be what? Would be 2A. Okay. When we get to add ammonia plus hydrogen sulfide. Those are the only two gases we have, remember, so 2A. And then the partial pressure, you can now find the partial pressure of each. So if we look at ammonia, the partial pressure of ammonia is basically 1 over the total. Let's just forget about the A, it's unnecessary. The total number of moles we have for the gases, it's 1 plus 1. So total number of moles is basically equal to a 2. So if I were to find the partial pressure of ammonia, it would be 1 over the total, which is 2, multiplied by what? Multiplied by the given total pressure, which is 0.658 atm. Okay, so that would give us a value of 0.329 atm. So we found the partial pressure of ammonia. This is for ammonia. And then we can also try to find the partial pressure of hydrogen sulfide. It's also going to be the same since it's 1 1 1. Since it's half half for this case, the calculations will just be the same. Zero point 0.329 atm as well. Now if you're able to remember, we said our Kp value in this case is only dependent on these two gases that we have. Our products, which is, we said, the pressure of ammonia multiplied by the pressure of what? Hydrogen sulfide. So we'll just substitute 0.329 multiplied by 0.329. Okay. So therefore the Kp value becomes, when you multiply the two, 0.1082. Okay, so that is our Kp value for this question. So if we add the gas there, of course, would have divided by its partial pressure. Okay, so that's the end of question 2. We're now on question 3 and 4. I had to put them on the same page. Here we are dealing with the Ksp value. The Ksp value deals with solubility, equilibrium, a component of chemical equilibrium, but it does stand independent, of course. So calcium sulfate, the solubility has been given to be that. We have to determine the Ksp value. Okay, so for all equilibriums that we deal with, there is, what you need to know is that we are able to write the K expression. Okay, so for the solubility equilibrium, basically what happens is you have to write down the dissociation reaction. Okay, we always start with a solid, and then what we basically get is it will split into aqueous states. Okay, so what are the ions that it will split into for the first one? So you can see that we've got calcium ion and sulfate, right? Now these, for this to be in the ratio of 1, we know calcium is from group 2, so it's 2 plus. Now for this to be in the ratio of 1 to 1, it implies that was 2 minus as well, which you should know. So the last two, the products, are in the aqueous state. That's one thing that we know clearly. Okay, so let me just write that down where we have enough space here. So what do we have? We have calcium sulfate as a solid dissociating into calcium 2 plus ions plus sulfate ions. Okay, now we've been given the solubility. Now if I was to show you something that we basically, there's a formula that we actually use here. Of course, if you want, you can go on and write the ice table, but at times I feel it's not necessary for this specific question. I feel there is a better way that we can actually handle it, a faster way, where of course we know that the solids and the liquids do not appear in the K expression of the ice table. They wouldn't appear as well. So if we were to write the ice table, the alternative would be look at the coefficients here. They both have ones, so we can just put plus x plus x. Of course, if you're new to this as well, you can watch a full video. It's available. Solubility equilibrium. What we basically do is we just write plus x, indicating that this is actually supposed to appear on the change. On the change, you put plus x, indicating that these are going to increase. Well, for the I, that denotes the initial, and then we'll put zeros because initially we didn't have any of the two. To find the equilibrium, we add the initial and the change. So these will still end up being x. If we added 2 there, the case would be different. It would end up becoming 2x plus 2x. Well, under chemical equilibrium, we talk about the presence of reactants as well. For the reactants, for the change, we put a negative. I'm sure you know that by now. Okay. So therefore, for our KSP value, it's going to be dependent as well on the products over the reactants. The products, we just ending up with x and x for the equilibrium expression, like for the equilibrium concentration. So it's x to the raised to a stoichiometric coefficient, which are still ones, multiplied by x to the power 1. For the KSP, we start with a solid, so it doesn't appear in the K expression as well. So our KSP value just becomes x squared. That's why it's possible to predict even without the ice table, because we know that we don't have reactants appearing in the expression. So how do you do that directly? So when you've come up with an equation just the way it is, okay, so look at the coefficient. Since it's 1 and 1, just say x, then raise to the power 1 and 1. If we had 1 raised to the power, let's say with a coefficient of a 2, it would have been 2x, and then multiplied by the other one x, and then this 2x should equally be raised to the power 2. That x should be raised to the power 1. Okay, that's the difference. And then what it gives you after multiplying is the KSP expression. Now what is the KSP expression? In this case, we've said it's x squared. Now the x is what denotes what we're calling the solubility. So we just substitute 5.0 times 10 to the power negative 3. That is the power 2. Okay? So what do you get when you square that? So we're going to have 2.5 times 10 to the power negative 5. That is our KSP value. Okay. So if you've noticed, I'm not adding units to the K values. Now, feel free to pause the video and try out the second one based on the same concept. So we have that, and then we want to write the dissociation reaction. Pause the video and try it out. So one way that you can actually determine is by splitting the 2. This is the power to the subscript 2. So this implies, since there is nothing on the SR, it implies there is a 1 there. So when you take back that's there and the 2 back there, those will give you the charges, right? So that would be S2 plus, and then plus F. Of course, we know it's coming from group 7, so that's a negative 1. Instead of 1 is supposed to be positive, the other one is supposed to be negative. This is an aqua state, aqua state. Well, is it balanced? Of course not. So fluorine still needs a 2 there to balance it up. Now the equation is balanced. So I gave you a shortcut. KSP is going to be, this is x because of the coefficient of 1, that is 2x. Now I also did say, what did I say? The power 1, again that the power 2. So our KSP expression becomes x multiplied by 2x squared, that's going to be 4x squared, which gives us 4x to the power 3, right? You can now substitute our x, 12.7, right? Now if we look at the 12.7 again, there's something funny about it. The units are not in what? We want to deal with solubility in terms of molar concentration, so we can't just substitute directly. I almost forgot that part there. Okay, so let's convert that to molarity. 12.7 times 10 to the power negative 3, that is in grams, and then we are saying we're dividing by 100 milliliters. Okay, so I want to convert that to molar concentration. What do we do? First of all, we need to convert the volume, which is in milliliters, to liters, right? So 1,000 milliliters, okay, 1,000 milliliters is equivalent to a liter. So that in itself would have helped us convert to liters already on the bottom. And then we can multiply by to deal out with the grams, or to help us find the number of moles actually, we can use the molar mass of that. So grab your periodic table and find the molar mass. Okay, you're free to pause the video. We have done that. What I'm getting is, I'm getting 125.6188. So that is grams per 1 mole. So let's try to perform some dimensions analysis here. The milliliters will cancel, the grams will equally cancel, so you remain with moles per liter. Okay, you can cancel a few zeros as well to make it easier. So 112.7 times 10 to the power negative 3 multiplied by 10 divided by 125.6188. The value I'm getting is 1.011 times 10 to the power negative 3. So I said solubility represented by X should be molar concentration. So that's where that comes about. Okay. So feel free to pause the video and perform the calculation. Some people, we actually need some practice. Some people need practice when it comes to these calculations. So you're at liberty of pausing the video. Okay. So I'm also performing that calculation. 1.011 times 10 to the power times 10 to the power negative 3, and then that itself raised to third power multiplied by 4. Okay, so the value of the KSP, what I'm getting is 4.13 times 10 to the power negative 9. So that's for question 3 in full. Now question 4, you're given a 0.10 molar concentration solution of a weak monoprotic acid. So this is now coming from acid base equilibrium. Okay, so we are given the pKa, so that's also an omission there. So that's supposed to be pKb. This is that's pKa. You're given 0.1 molar solution of a weak monoprotic acid with the pKa for its conjugate base. Okay, this pK value belongs to the base, so let's call it pKb instead. Sorry for that omission. Calculate the Ka value for, so that's pKb, for the HB acid and the pH of the 0.10 molar concentration of our acid. So let's take note of the data that we've been given for this question to make sense of it. So we've been told the concentration of this acid is 0.10 molar concentration. We're also told the pKb value for its conjugate base, B, is 4.13. Okay, and then they want us to find the Ka. and then they also want us to find the pH at the end of the day. So one thing that we know that can help us, since we've been given the PKB can help us find the KB. One thing that we know is that the KB is actually equal to 10 negative PKB. Okay, that's a relationship that we basically know of. So we can find the KB by substituting. So that would be negative 4.13, and our KB therefore becomes, we can just actually just leave it at that point to avoid complications. Okay, since we're going to use that value. Then the other relationship that we know from our acid base is that the product of Ka and Kb, so meaning that the Ka of the acid and the Kb of its conjugate base basically should be equal to, at 25 degrees of course, since no piece of information has been given, the product of the two is 1.0 times 10 to the power negative 14. Okay, so our Kb value is known. We can find our Ka by just dividing the Kb. Now Kb is 10 to the power negative 4.13. So the Ka value that I'm getting, 1.0 times 10 to the power negative 14 divided by 10 to the power negative 4.13 is 1.35 times 10 to the power negative 10. Okay, so we've answered the first part. Okay, so in summary, the things that you have to know is the pKa, or in this case we're dealing with the pKb. The pKb or the pKa, the pKb is basically equivalent to the negative log of Kb. Okay, this is a functional relationship, so you have to know that. Okay, just like we say the pH is also equal to the negative log of the hydrogen concentration. If you say the pOH as well, the pH is also equal to the negative log of the hydroxide concentration. So equal even the pKb is that. So from here, this is where we built the relationship to say, if we divide both sides by negative, we get negative pKb. Of course, it's supposed to be a bit lower. Negative pKb and then log Kb. We know this is base 10, so we know logs, it will become 10 to the power negative pKb, and then that is equal to Kb. That's where this relationship came from, the one that we utilized to help us find the Kb value. And then we're also saying Ka multiplied by Kb is 1.0 times 10 to the power negative 14 at 25. We've utilized that to help us find the Ka value. Now, can we find the pH of this solution? Okay, so the acid we're given is Hb. So what do we know from roasted lolly? What do we know about an acid? An acid is a proton donor, right? So proton will be donated to lose the hydrogen, and then so there will be that separation between the two. So the B minus is going to be called the conjugate base. Okay, this is the acid conjugate base. So what do we do now? We're trying to find the pH. Now the pH, as we know, is dependent on the concentration of the hydrogen, or the hydronium ion if you want. So how do we find that concentration? We've been given the concentration of the acid at start. So let's come up with the ice table. So the concentration at start was 0.10. For the products, we didn't have anything at start. For the change, all these are having coefficients of 1. So for the reactant, it's negative, implying reduction it reduces as the reaction proceeds. And then for the products, they were all forming, so we'll say plus x plus x. And then the equilibrium is going to be the addition of the two. 0.10 plus negative x, that will be 0.10 minus x. This will just be plus x, that will be plus x. So therefore at that point we've got the K expression. Okay, since it's the K for an acid, we'll call it the Km. Well, don't forget what we had for equation. This is the acid, and then these are the products here. So our products, H plus raised to the power 1, B minus raised to the power 1, divided by our reactant. So all these were in aqueous state, so they all do qualify to appear in the expression. So that would be x multiplied by x, and then we only have one value that we can actually substitute, which was 0.10 minus x, also raised to the power 1. The K value is 1.35, which we had calculated. Okay, and that is x squared over 0.10 minus x. So at this point, what do we do? Okay, so we'll use the 5% rule. We know that whenever we've got an addition or subtraction, at this point we don't want to end up with a complicated quadratic equation. That would be a sheer waste of time. So since the K value is low, we'll cancel the minus x. If it was an addition on top as well, we would have cancelled it out. Okay, if you want, you can perform this at your own time. You see that it actually does not make a difference. Okay, so cancel that, and then just try to find the value of x. So x squared is going to be equal to 0.10 multiplied by 1.35 times 10 to the power negative 10. So our x is going to be a square root of what's on the right. Okay, so what do we get as our x value? That's 3.67 times 10 to the power negative 6 molar concentration. Okay, so that is basically what we've gotten there. What are we trying to do? We're trying to find the pH. Now the x value, if you get back the ice table, just that I didn't have enough space, the x values were representing what? The hydrogen and also the conjugate base. So we know that we are confident x value is representing both of them. So therefore our pH is actually dependent on the negative log of the hydrogen concentration, which is the same value, 3.67 times 10 to the power negative 6. Okay, so I'm getting a value of 5.44, which is of course for a weak acid. Okay, so that's it for question 4, right? That's from acid. That's what acid base equilibrium basically deals with. Okay, now let's proceed now with F5 and A6.